All right, back from the weekend. So starting this Monday off with doing exponent rules. Exponent rules is an easy concept to learn, but for some reason there's areas where students struggle. So I just want to go over some basics of exponent rules, and I'm gonna try to give you the most common sense approach that I know. All right. All right, so on this board, I have 2 to the third power. 2 to the third power. The 2 represents my base. The 3 represents my exponent. And the whole thing is called a power. All right. So you have the base, you have the exponent, and this expression itself is called a power. Now, you can look up the mathematical definition in any textbook or glossary, Google it or whatever. But basically, when we're talking about powers and exponents, it's basically repeated multiplication. That's all it boils down to. You're just repeating your multiplication. So what's important to know here is that this has a meaning, all right? So 2 to the third power has a meaning of 2 times 2 times 2. There's your repeated multiplication, 2 times 2 times 2. So here's the first example. I have a 2 to the third power times 2 to the fourth power is equal to 2 to the blank, or 2 to the question mark power. All right, now, so I'm going to talk about this from a common sense approach and the meanings. So if you understand the meanings, the rules make more sense. The rules are really a generalized statement for what we were able to find based on patterns, right? So I'm going to start with how the meaning works and then go into the generalized rule. Maybe it'll make more sense. So like we talked before, 2 to the third power is repeated multiplication, which is 2 times 2 times 2. That's 3 times, right? Now I'm multiplying 2 to the third power times 2 to the fourth power. So that means 2 to the fourth power is repeated multiplication. That's 4 times. 1, 2, 3, 4. So if we take a look at what it's asking us, it wants to know, okay, this is 2 to the what power? And the answer comes when you count all of these up. If you got a third power over here, then you got this fourth power over here. If you add up the 2's, you got 1, 2, 3, 4, 5, 6, 7 of them. So basically your answer or your question mark should say 2 to the 7th power. And that's pretty much how this exponent rule works. Now, it's a couple of things I'm going to point out. This is multiplication, and these 2 have the same base. All right. So we can't add 2 to the third power, and this was like a 5 to the fourth power, and think we're just going to add it up and get one result like this one. This does work when your bases are the same. So now when we start looking at much larger numbers like 2 to the 18th power times 2 to the 25th power, we understand there's a repeated multiplication just like that one is. But why would we repeat this out on paper 18 times and then do that one 25 times? Like, you wouldn't even have enough room on your line of paper to even stretch that out or expand it, right? But if we know what happened with the last one, and remember the last example, we had 2 to the third times 2 to the fourth. That was 2 to the 7th. So now we understand the meaning. But now, remember, mathematics, we try to look for an efficient way to get to our solution. And if you understand there's a relationship between your numbers, therein lies a way you can generalize it so that it can become a little bit quicker now. So if I had 2 to the third and 2 to the fourth multiplying each other, and my answer was 2 to the 7th, you should start thinking about, okay, there's a relationship between 3, 4, and 7. And that relationship has to be addition. All right, so there's the relationship between those exponents now. Really, all I have to do is add the 18 plus the 25, and now I have 2 to the 43rd power. And I'm able to write 2 to the 43rd power without having to write these down 18 and 25 times. Now you can just use addition to simplify your problem, and we're working with an extremely large number. All right, so here's your rule. I gave it to you verbally in the previous slide. Look at there. Same base, add exponents. And what are we doing? We're multiplying powers of the same base, add exponents. And that's why we have the base written once with the addition on the exponents. That's what that rule is saying. Now, don't get too bent out of shape when you see these letters. I can use any letter I want to represent the statement that I just made. It doesn't have to be A to the M, A to the N. I could have used P to the Q times P to the S. So those are just letters, but the placement of those letters is what you have to pay attention to. So as long as these bases are the same, you can add these two up if you're multiplying. That's what the rule is saying. So the next one coming up is going to be division of powers. All right, division of powers. We just did multiplication of powers. Now we're going to look at division of powers. The same thing. We're going to look at a common sense approach based on the meaning. Then we're going to look at the rule after that. 2 to the fourth power divided by 2 to the third power is 2 to the blank power. We're going to look at that one based on the meaning first, and then we're going to go from there. Yep, so 2 to the fourth power. Notice in the top, I have 2 to the fourth power. That's why I have the repeated multiplication 4 times. The denominator is 2 to the third power. Look at the bottom. I have repeated multiplication 3 times. All we do at this point is simplify. Anytime you take a number divided by itself, its result is 1. So I'm going to go through and start finding all my 1s. That's equal to 1. That's equal to 1. And that's equal to 1. So basically what I'm looking at is a 1 times 1 times 1 times 2. So the final answer is 2. Everybody see that? The final answer is 2, also known as 2 to the first power. Yep, so your final result is 2 to the fourth power divided by 2 to the third power is 2 to the first power. So there's a relationship between those numbers that we're looking at, like 4, 3, and 1. There's only other one option you can think about, and that's subtraction. 4 minus 3 is equal to 1. Therein lies your general statement. So we have division of powers with the same base. That means you can subtract exponents. Same base, subtract the exponents, and that's why we have A with subtraction on the exponents. There we go. We got it now. That's your general statement based on the patterns with the numbers. So I have 2 to the fifth power divided by 2 to the seventh power. So I repeat my multiplication 5 times across the top with the number 2. Then at the bottom, I repeat my multiplication 7 times with the number 2. So remember, once you do that, you look for all of your 1s. So here, that's equal to 1. That's equal to 1. That's equal to 1. That's equal to 1. And that's equal to 1. So I have a 1 times 1 times 1 times 1 across the numerator. That's easy. The answer is 1. All right. That's the numerator. The answer is 1. But if I look across the denominator, those are the only 2 left. So what I have is 2 to the second power. I'm not really writing the results because my whole point of this video is to pay attention to exponents. So I leave it as 2 to the second. You could write 4. That's the same answer. But the point is we're trying to make sure we evaluate the exponents. So any questions right here? That should be straightforward. We counted out, found all of our 1s, and then we wrote down what was left. 1 over 2 to the second power. So the rule itself says that I can do this. Remember, I have the same base, and I can subtract my exponents as long as I'm doing division. So if I have 2 to the fifth power divided by 2 to the seventh power, basically I can just run my same rule that I ran before, and then I have my 2, and then I subtract 5 minus 7. 5 minus 7. And what that gives me is a negative exponent. So that's the one thing I do want to talk about now is a negative exponent. All right, so we got a negative exponent. The one thing that I hear students say all the time and a lot of misconceptions happen is I thought you cannot have a negative exponent. So you can have a negative exponent. You just need to understand what they mean. And based on what we just did, you know what it means, but I just need to make sure that I connect it real. So this is the same problem, right? When we worked it out based on the meaning, we were able to go through all of this to come out at the end right here. Now, when I followed the rule, I come down here and follow the rule, and now I have a 2 to the negative second power. Basically, what this is saying is 2 to the negative second power, right, because of the negative exponent, is equivalent to that one over there. They mean the same thing, all right? They mean the same thing. So when you see a negative exponent, you can rewrite it as a positive exponent, but you're going to have to inverse the number. In other words, you have to turn it into like a reciprocal before you change that sign. And that's why these two represent the same thing. They just look a little different. So here's your general rule for the negative exponent. If you have the negative exponent, you can switch places so that it's down here at the bottom, or vice versa. It just depends on where it starts. Now you can get rid of the negative sign, but it has to switch places before you get rid of that sign. So you can move negative exponents from bottom to top or top to bottom, but whenever they change from bottom to top or top to bottom, you can now remove that negative sign. So that's basically all that's saying. Okay, now I have 2 to the third power raised to the fourth power, and that's equal to 2 to the blank. So we're going to base this off of the meaning first, then we're going to look at the rule. Based on the meaning, I get to repeat this multiplication 4 times. That's why I have it written down 1, 2, 3, 4 times. But if I look at each individual one, that means I can repeat this one 3 times. That's why I have a 1, 2, 3. I have another 3, 1, 2, 3. I have another 3, 1, 2, 3. Then I have another 3, 1, 2, 3. Now, if you count up every last one of those 2s, I have 12 of them total. So now I get 2 to the 12th power. Based on the meaning, that's what's going on here. As you can see, there's a lot of expansion going on. And if you get to the bottom of it, you can count it all up for 12. So we have to come up with a better way of doing something like this. Like, if these numbers got much larger, like double digits, you wouldn't have time to write that out a whole bunch of times, plus each time write those out again, right? So the numbers become much larger and they're more complicated to deal with if we just base it off of our understanding of what they mean, right? It's good to understand it at the lower numbers so that you kind of get a gist of what's going on here, but this is how you start focusing in on relationships and how these rules actually work. Now, if we pay attention to the beginning of the problem, I have a third power being raised to the fourth power. But at the end, look at my final number, 12. So if I have a 3, a 4, and a 12, the relationship between those two numbers have to be multiplication, because 3 times 4 is 12. And that's where your general statement comes from. If you understand that, you don't have to go through all of this expansion anymore. You can just evaluate the numbers themselves. And there it is, 2 to the third power raised to the fourth power. All we have to do is multiply the exponents and then get the 12. There's your rule. All right, so here's my a to the m power to the n power. So if you raise a power to a power, you can multiply the exponents, and that's why we have m times n. The way I remember it is when these two sit right next to each other in parentheses, kind of like that, you treat it like you would any other two numbers in parentheses. You multiply them. And that's how you get that one straight without confusing it with your other rules.